Right, hi, I'm Jeff Ringenberg. I teach an introductory programming course in the College of Engineering, and the work that I did is basically trying to figure out if I could write a predictive survey that would help us decide whether or not students should take my class or an advanced version of the class. So we call it the Programming Performance Prophecies. So all the engineers at U of M are required to take a programming course. So they come in and they take a class on how to program for computers. Most of the students take Engine 101, which is just a basic programming course where they learn C++ and MATLAB, and this is the course that's pretty much for everyone. But there's a subset of students that take an advanced class, and these are for students that are either experienced at programming from high school or they have a certain adeptness at computer programming. The motivation for this exam is that the incoming class of students has a very wide range of experience. We used to find that the students that were programming in high school did really well in the course and really demotivated the students that had never programmed before. And so computer science still isn't sort of a priority in high schools. In fact, it's almost a depriority in a lot of cases because it takes away from other electives that students could take. So we wanted to figure out some way that we could identify these students and separate them into the appropriate course, whether they should take 101 or 151. Previous work has been done in the past, looking at GPA, ACT, SAT scores, personality traits, math aptitude, all sorts of different things that these students have had in the past. And a few correlations have been found to exist, in particular between math scores and so on and so forth. But this kind of data is kind of hard to deal with. All right, we don't want to have to go out and search for all their ACT scores, their high school GPAs, their grades in a specific math class in high school, so on and so forth. We want to just give them a basic, simple survey that tracks their potential performance in the course. So we want it to have low overhead, and we want to be able to give it to them during their summer orientation or in some sort of fashion before they come into summer orientation. So, for example, calculus does this to decide whether or not students should take like the remedial calculus or the intro, college pre-algebra, whatever, to figure out where they're supposed to go. So we want a similar exam. Now the questions that we're going to give them have to be programming language agnostic. They can't have C++, they can't have MATLAB, they can't have Java or any of the other programming languages out there. They have to be focused purely on algorithmic math and logic, computational style thinking. And so we basically sat down in before fall 2009, sort of in the summer of 2009, and came up with a list of questions that we thought would be useful. So that was where we did the initial release of the exam, was in fall 2009. We had about 350 students that we did this with. And then we did an analysis of that. We refined the questions. We picked the ones that were good, and I'll talk about that refinement process here in a second. And then in fall 2010, we took the refined questions and we gave it to a new class of 450 students. And this included students from the accelerated course as well, to see how they would do on the questions. And then we did another analysis at the end of that in winter 11. And then in fall 2011, that little step's not on here. In fall 2011, we did another version of this. So this was just last semester. And we did an analysis of that data as well to see how well we could predict student performance. And then we came up with essentially a set of 3 numbers that we gave to the orientation staff in the Office of New Student Programs, and said, you know, if a student gets this, tell them to take 151. If a student gets this, tell them to take 101 if they've had prior experience. If a student gets this, tell them to take 101 regardless. And we're still working on the very end of the tail, whether or not we should say this student isn't even ready for 101. And it might not even be possible for this survey to do it. Right? The survey only has 16 questions on it, so it's not a super long survey. But it does, from what we've found, have a good ability to predict the students that are going to be sort of at the top of the scale. All right, so the correlation analysis that we did to decide whether or not these questions were useful was sort of an ad hoc approach that was actually developed by one of the undergraduate students that were working with us on this. So the first thing that we did is we took any of the questions that 80% of the students got correct and we just threw them out. So the original exam from fall 2009 had 25 questions on it, and we wanted to get that shorter. We didn't want the students to be spending an hour on this exam. We wanted them to spend at most 45 minutes, but more on the average of about a half an hour. So we took those questions that 80% got correct, we tossed them out, and then we moved on to creating what we call question sets. So we took questions and we lumped them into sets of 7. And the reason we did this is because we didn't want to try to correlate specific questions to overall performance in the course. We wanted to sort of lump them into groups. So we took 7 questions in each of these sets, and then we correlated them to the overall course grade. So if a set was correlated above, I believe it was, 0.4, we considered that to be an effective set. And then what we did is we took of all the effective sets, how frequently did effective questions occur in those sets? And so we came up with a percentage of effective sets, a percentage of effective sets that effective questions occurred in, and we came up with a graph that looks like this. So this graph right here has questions 1, 5, 6, 10, 12, 14, 18. The ones that are missing were the questions that more than 80% of the students got correct, so they didn't even show up. The red line shows what percentage of the students got it correct. So you can see it sort of peaks out at around 80%. And then the blue bars represent how frequently a question appeared in effective sets. So a high blue bar means that the question was effective, less than 80% of the students got it correct, and also it appeared in a lot of those effective sets of questions. So it was basically, involved in a lot of these highly correlated sets. And so what we're looking for here is we're looking for a question with a high bar and a low red line. Not too low, but a fairly low red line so that it can be used as sort of a discriminating type of question. So questions like 5 and 19 and maybe 22, those are the types of questions that we're looking for. And so we pulled some questions out of fall 2009. We ended up only keeping 5 from fall 2009. And then we mixed them in with some questions that were what we consider to be more appropriate for the fall 2010 data. And we did the exact same analysis on this. And so of the 2009 data, there's 5, 10, 13 of the 25 were considered useful. In fall 2010, all of them showed up as being useful, except for maybe number 9. That barely was there at all. But most of them had an occurrence rate of around 40%. A few of them were a little bit less, but they all sort of showed up as being effective questions. In fall 2010. And so then this exact set of questions was then used again in fall 2011. And then from that data then we did some correlation studies. We correlated the fall 2009, which is the original 25 questions, which weren't very good. And we found that overall course grades were correlated by 0.33 to their score in the survey, which for something like this we deemed was pretty good. And then when we moved to fall 2010, the correlation went up to 0.39. So the questions were, in a sense, better at correlating to overall course grade. And that was it for just the sort of data trending. It turns out in fall 2010, we also had some numbers for the advanced course, and those were actually more highly correlated, 0.48. So the students there did a lot better. So this is sort of the first half of the work. Then we went and took those numbers and we plopped them into some ROC curves to decide, like, was there a good point at which we could say if you get this score, you're more likely going to want to take 151 than 101. So this is the data from fall 2010. And ROC curves, I'm not a stats geek, so I don't really know about them too much, but I do know that they tell you if you have a binary classification system, in other words, you're going to tell a student to take 101 or 151, or more appropriately, not take 151 or take 151. An ROC curve is going to tell you, is that system effective? Does it maximize, let me see the terminology here. Does it maximize sensitivity and minimize 1- specificity? You're trying to get rid of false positives and false negatives. Okay, you want to make sure that you're not telling somebody to take the course when they should, and you're also wanting to make sure that you're not telling someone to not take the course when they should do it. It's a lot of confusing words here. So basically, you want a perfect curve for the blue line here. You want it to go straight up and then straight across, which means that every single person you gave advice to got the perfect advice, and they shouldn't have gone the other way. So looking at the numbers from fall 2010, which had this curve, and a recommended survey score of around 11 or 12 out of 16, and then looking again at the scores from fall 2011, which had a different shaped curve, but they're both sort of squarish, which means that it's a fairly good result. The one from fall 2010, the score was around 11 or 12. Up here, it's around a 12 or a 13, where we can sort of get as much sensitivity as we possibly can, while also minimizing the 1 minus the specificity. And so, using those numbers, I'm going kind of fast because I got to get to office hours at 1 o'clock. Using those numbers, I came up with a suggestion that we then threw at the folks from the Office of New Student Programs. So we said, at first I said, the turning point is going to be 14 out of, the border between 13 and 14 out of 16. No, that's why I picked finally. Before that, it was the border between 12 and 13. So if a student got 13 or above, we'd tell them to take the accelerated course. And so I threw it into this little matrix here, and I came up with all the different numbers. We had to scale the data from fall 2010 because we missed a section. So the important numbers are the ones that are sort of in the yellow and whatever cream colored things here. What we're looking for here is we're looking for if we expect 1/7 of the students that we give advice to take 151 to take 151. In other words, they have prior programming experience, and we suggested that if you have prior programming experience and you scored between 11 and 13 inclusive, you should take 151. Then we get a class size of between 69 and 114. The fall 2011 students did better. All the scores down here show that. The mean in fall 2011 was 9.7, it was 9.3 in 2010. It was 13 for the accelerated course in fall 2011, and it was 11.8 in the 2010. So these numbers here for 2011 show that the class sizes would be bigger because they did better on the survey overall. So what we basically did here is we're trying to anticipate, and this is sort of where we're at right now in the research. We're trying to anticipate how many students are going to take our advice. We're assuming that all the students that got greater than or equal to 14 questions are gonna take the course. I believe that's mentioned right here.
Assume that there'd be a drop in the average for the lower level course, or is that not?
Yeah, so we would expect the students, so the students right now that took 151, the advice to take 151 was simply, have you ever programmed before? That was it. And that isn't the kind of metric that we want. We want a metric that says, even if you haven't programmed before, you might actually be inclined to be good at programming. I mean, it's obviously a good predictor because it showed in the survey results. The students who took 151 based purely on that advice did better. But we want to be able to pick up those other students that might not have programmed before, but have a natural proclivity to program. So, yeah.
So what were some of the best discriminating questions?
The best discriminating questions, we can sort of look at them. Let's see here, presentation. So the best ones were like question 4 and question 13. So I don't have the question list, but I can pull it up real quick. This was published last summer at ASEE. Question 4 was this. What does this list of instructions do? And so this looks kind of like a program. It uses iteration. While x is greater than or equal to y, assign x minus y to x, return x. So this is an algorithm that essentially returns the integer remainder of the initial value for x divided by the additional value for y. So this tests their ability to think algorithmically. Normally when you tell a student that this line of program that says x equals x plus 1, they don't understand what that means. There's no possible way that x can equal x plus 1. That doesn't fit into my brain. But when you think about things as having some sort of time associated with it, execute this instruction, then this instruction, then this instruction, x equals x plus 1 simply says just make x 1 bigger after that line goes.
So the questions are basically pseudocode?
Yep,
You say,
exactly.
Please interpret pseudocode and tell me what you think it does.
So the first, let's see, the first 6 questions are pseudocode. And then there's some logic questions about buying horses and calculating exterior surface of cubes and things like that. And then the other question that was highly effective, interestingly enough, was a question about base 2 math or binary arithmetic. So we asked them to add 2 numbers in binary, and some of the options were if they were thinking in base 10, and the correct answer was if they were thinking in binary. So this is the answer in binary. And that was question 13. So on the results for question 13 was way over there. Only 45% of the students got it right, and it was in 80% of the effective sets.
Did you try something with hexadecimal?
No, but we could. So one of the future work things of this is to every year at orientation to sort of do the genetic algorithm approach. Throw in a couple of extra little things that are sort of mutated on these questions, and then rerun the analysis every year and see if those new questions are better, and then prune out the bad ones. Question 9 is a question about tic-tac-toe. How many squares are in a tic-tac-toe board? So that's got two issues to it. One, international students might not know what tic-tac-toe is. And then two, it's really sort of out there. Oh, there's 9, obviously, but then you have to sort of draw this one and then the bigger one and then the whole bigger one. It was just poorly worded. Unfortunately, we had to get the questions to the Office of New Student Programs for this summer, and so it's going to be there. But, in future, in general, yeah.
Is it, I just want to see if I can have this pretty clear. You came up with the questions and you grouped them in all these different groups, which is something like fractional factorial analysis, or if that doesn't mean anything, I think it is.
Okay.
But then once you knew that you had a question that appeared frequently in an effective set, was it okay then to take and regroup those questions? That's what you did?
Yeah, so as long as a question,
You get a lot of measurements, but then once you identified the effective question.
yeah, so that was what we did in moving from 2009 to 2010. So in 2009, we took the high percentage bars, like 5, 6, 19, 22, and we included those in the questions for fall 2010. So the paper that we did, where is it? It's right here. Here. So these are the questions in the Appendix B. Questions 1 through 11 were all new. And then questions 12 through 16 were the ones from fall 2009. So like questions 6, 19, 5, 22, and 12 were questions that came from the previous year. Those were the ones that were the best. They were in the most of the effective sets. That's it in 5, 10, 15 minutes. Yeah.
There's a discriminator for students to have math before they go into 101 or 151. Is that factored in here at all?
I don't know if it's actually, is it a prerequisite or is it a concurrent?
It's not a formal prerequisite, but the advising office is
Oh, really?
rather than college.
Okay. We haven't really considered that at all.
Is it for 150?
Before people take engine 101 or 151, one of the discriminators is that they have math 115.
Okay.
That's an active,
Okay.
an active filter. That's not actually documented in the prerequisite.
Okay. So
That-
we didn't know that, but okay. Okay. Yeah, this will be given during summer orientation now, before that discriminator is in place. So if they take it in the winter, these are only fall term things. So the discriminator applied to them in the fall. But when they take it in the winter, their survey scores, presumably if 115 helped them, would be
I just
lower.
don't know where that other filter kicks in. Whether
Yeah.
This kicks in first or the other filter kicks in first.
Oh, I see.
So I know this because out of engine 100, there's a big difference, a third of a grade to a half a grade that occurs because of this discriminator in math ability, whether somebody takes it in the fall or somebody takes it in the winter. There's a noticeable disparity there,
Okay.
and that
Maybe that'll show up in our results, because now that we're doing this in the summer during the orientation, we'll have data for both. For this was just fall data, and because we only polled the students who were in our courses in the fall. But if we give it to all the engineering students, we're going to capture them all, and then we can correlate it to their scores in the winter terms as well. So that'll be interesting. The only issue there is that they will have had a semester of being a Michigan student.
Yeah,
And-
there's other
yeah,
factors.
yeah.
This was an unadvertised filter.
Yeah.
That, I discovered it inadvertently.
Okay, I'll have to keep that in mind. Thanks. Yeah.
So is the analysis all done with the whole group, or are there some gender-specific analysis?
Whole group. Yep. We didn't have any of the gender data or anything like that. But at a SLAM session, it would be nice to include all that.
I think this is a great way to, use data to tell you about what really is discriminating, and to do it in a live way like this is really excellent. So I think it's a really good approach. Your point about having an advisor say, "Have you ever programmed before?"
Mm-hmm.
I mean, and that's one of the kind of classic ways we give advice. Did you take physics in high school? But there's a huge range of what it means to take physics in high school or have programmed before. And if you don't know any more about it, you're really missing a lot. And this, a test like this can get at it, or deeper questioning of the student can get at it. But knowing more about that's really important.
Yep.
Some students will say, I had the greatest class of my life in physics. Others will say my physics class was a joke, and they know it was. And it actually puts them maybe in a worse place than someone who's never taken it.
Yeah, like my high school physics class.
Well, there you go.
It's a joke. All right.
Any other questions? No, thanks a lot for
Great.
coming in.
You're welcome.
Very good.